Hello everyone, this is an audio recording for the visually impaired student from the book Organic Chemistry Volume 3 by Dr. S.N. Dhawan. Organosulphur compound. Introduction. Sulfur is placed in the third period of the periodic table, just below oxygen in group 16. During the recent past, a lot of work have been carried out in the area of organosulphur compound, primarily due to their importance in industry, pharmaceuticals, and metabolic processes. Therefore, in this unit, we shall discuss some important aspects of the chemistry of organosulphur compound. Structural features. Both oxygen and sulfur alter the chemical nature of carbon atom to which they are attached. But unlike oxygen analogous, in most of sulfur compound, the reaction occurs by the attack of a nucleophile and electrophile or even a free radical at the sulfur atom. Another marked difference between oxygen and sulfur compound is that unlike oxygen, which readily form double bond, sulfur is reluctant to form double bond by pp overlapping. Thus, with the exception of carbon disulfide CH2, thiocarbonyl compound R2C double bond S are quite unstable and readily undergoes addition reaction. In other words, aldehyde and most of the thioketone can be generated only by transient intermediate that rapidly undergo dimerization, trimerization, and polymerization to form compound having only sigma bond. For example, a thiocarbonyl dimer, a thiocarbonyl trimer. The instability of the thiocarbonyl compound is primarily due to the difference in the size of the 2p orbital of carbon and 3p orbital of sulfur, which make 2p 3p overlapping relatively ineffective. In addition to 2p 3p overlapping, sulfur is also reluctant to form 3p 3p pi bond with other sulfur atom. It is because of this reason that elemental sulfur does not exist as diatomic S2 unlike oxygen molecule. Instead, it prefers to form only SS sigma bond and exist as a non-planar octatomic molecule acid having crown shape as shown in figure 3.1. Figure 3.1 non-planar 8-membered ring structure of elemental sulfur acid. Further, due to the larger size of sulfur atom, SS bond is quite large. As a result, the 2 3p orbital one on each sulfur atom cannot come close enough to undergo 3p 3p overlap to a significant extent, and hence the pi bond between 3p 3p orbital is very weak. It may be, however, be noted that unlike thioaldehyde and thioketone, thiamide and thiacids are isolable and hence are relatively stable. This contradicts the generalization that pi bond involving sulfur atom are very weak. The actual reason for their stability is the resonance stabilization involving lone pair of electron on nitrogen or oxygen atom. Here the contribution of structure 2 towards resonance hybrid of thioamide and that of structure 4 towards resonance hybrid of thioacid is significant because both of them have only single bond between sulfur and carbon atom. We have discussed above that sulfur has little tendency to form pi bond through pp overlapping. However, many sulfur compounds such as dimethyl sulfoxide DMSO, a widely used aprotic solvent, have a pi bond between sulfur and oxygen atom. As anticipated, this double bond, like any other double bond, consists of a sigma bond and a pi bond. The sigma bond is formed by head-on overlap between an sp3 orbital of sulfur and one of the half-filled p orbital as, say, 2px of oxygen. The other two sp3 orbital of sulfur overlap with 3p orbital of 2 alkyl group to form two additional sigma bond, while the fourth sp3 orbital contains a lone pair of electron. Sulfur is now left with a half-filled d orbital, say dxy and dxz, and oxygen also have an half-filled p orbital, say 2py and 2pz. Since dxy lie in the plane of 2py orbital and dzx lie in the plane of 2pz orbital, therefore d pi p pi overlap occur either between dxy and 2py orbital of or dzx or 2pz to form a pi bond. Structure 3.2 structure of DMSO and a three-dimensional B showing d pi p pi overlapping and C showing d pi p pi bond. In valence bond term, this p-pi-d-pi bonding implies that DMSO may be regarded as a resonance hybrid of the following contributing structure. Since DMSO has a high dipole moment 3.9 dBi, this suggests that the structure 1 makes a significant contribution towards the resonance hybrid, which of course is much greater than that of structure 3. An important difference between ordinary double bond with the p-pi overlap and sulfur oxygen double bond with p-pi overlap is that the group attached to sulfur do not lie in a plane. This explains why acetone is planar while DMSO is non-polar. Structure of thiol and thioether. Both in thiols and thioether, sulfur is sp3 hybridized in the ground state and not in the excited state as shown on page 103. Such a sp3 hybridized sulfur has two half-filled orbitals which overlap with the sp3 orbital of an alkyl group and a s orbital of the hydrogen atom as in thiols, or with sp3 orbital of two alkyl group as in thioethers. Each of the remaining two sp3 orbital contain pairs of electron. However, due to greater lone pair repulsion than bond pair repulsion, the carbon sulfur hydrogen bond angle decreases from 109 degree 28 minute to 100 degree in CH3SH. In contrast, in thioethers, due to greater steric hindrance between two alkyl group between than between an alkyl group and a hydrogen atom in thiol. The bond angle in thioethers is larger than in thiols. For example, methyl thioethers had a bond angle of 105. Structure of sulfonic acid. In sulfonic acid RSO3H or ArSO3H, sulfur is also sp3 hybridized. Since here we need to form two sulfur oxygen double bond, therefore both the 3s3p electron are promoted to d orbital as shown below. Electronic configuration of sulfur. In 3s, one electron is filled, and in 3p, one electron is present in one orbital, and in 3d, two orbitals are filled. The 4sp3 orbital of sulfur atom 4 sigma bond forms 4 sigma bond and 1 with the carbon atom of the alkyl or the aryl group and 3 with the oxygen atom. Sulfur is now left with two unhybridized d orbital which overlap with p orbital of 2 oxygen atom to form 2 d pi p pi s double bond o oxygen s double bond o bond. The p orbital of the third oxygen atom overlap with s orbital of hydrogen to form an OH bond. The sulfonic acid have tetrahedral structure as shown in figure 3.3 C. Nomenclature. For the purpose of nomenclature, sulfur compounds are classified according to the valence state of sulfur. The compound containing bivalent sulfur are structurally analogous to the corresponding oxygen compounds such as alcohol, carbonyl compound, carboxylic acid, etc. Therefore, they are often named by adding the prefix thio to the name of the corresponding oxygen analog. For example, thioalcohol, thiophenol, thioalcohol RSH, thiophenol C6H5SH, diethyl thioether C2H5S, C2H5, thioacetaldehyde CS3C double bond SH, thioacetone CS3 C double bond S bond CS3, CS3 bond C double bond S in SH, thio dithioacetic acid, thiourea NH2 C double bond S NH2. For forming the compounds having structure in place of carbon, having sulfur in place of carbon, the prefix thio is sometimes used. Thiocyclohexane 2,5-dithia-1,6-hexane diol HOCH2S CH2CH2S CH2OH. For compound having sulfur in the higher oxidation state, special named are used. CH3S double bond OOH, methane sulfonic acid, benzene sulfonic acid, benzene ring attached with S double bond OOH, paratoluene sulfonyl chloride CS3 C6H5 SO2Cl, CS3 SO2 CH3 dimethyl sulfone. Thiols or thioalcohol. Just as alcohol are alkyl derivative of water, in the same way Thioalcohol are alkyl derivative of H2S. Water, by replacing hydrogen and adding plus R, we get alcohol. Similarly, hydrogen sulfide, hydrogen atom is replaced, an alkyl group is attached, then we get thioalcohol. Thus, the general formula of thioalcohol is RSH. In the IUPAC system, thioalcohols are called thiol. They are also called mercaptan. Mercurium means mercury and captan means catching. Since they react with mercury to ion to form insoluble mercury compound Rs whole twice Hg, the functional group of thioalcohol is SH. It is called sulfhydryl thiol or mercaptan. A number of sulfur compounds are found in nature. For example, butane thiol are found in skunk and American animal. Propane thiol occur in onion. Allyl mercaptan and allyl disulfide occur in carne. Nomenclature of thiols. These are named according to the following system. First is common name. In the common name, thioalcohols are called mercaptan. The individual name of any thioalcohol is then derived by adding the word mercaptan to the name of the alkyl group. Second is IUPAC system. In the IUPAC system, thioalcohol are called thiols. The individual name of any thioalcohol is then obtained by adding the suffix thiol to the name of the hydrocarbon containing the same number of carbon atom. In case of isomeric thiol, the position of the SH group is indicated by the lowest possible Arabic number. The system and IUPAC, the common and IUPAC name of some typical thiols is given below. CS3SH methyl mercaptan, IUPAC name methane thiol. CS3CH2SH ethyl mercaptan, ethane thiol. CS3CH2CH2SH and propyl mercaptan, 1 propane thiol. CS3CH CS3 and SH. Isopropyl mercaptan, 2 propane thiol. CS3CH CS3CH2SH isobutyl mercaptan, 2 methyl 1 propane thiol. C6H5SH cyclohexyl mercaptan, cyclohexane thiol. HSCH2CH2SH 1,2 ethane dithiol. In case of polyfunctional compound, the thiol is named as the mercaptan derivative of the principal functional group. It may be noted that OH group is assigned higher priority both in numbering and naming. For example, HSCH2CH2OH, IUPAC name beta hydroxyethyl mercaptan and IUPAC name 2 mercaptoethanol. COOH C6H5COOHSH. M meta-mercaptobenzoic acid or 3-mercaptobenzoic acid. Method of formation. Thioalcohols are generally prepared by the following method from alkyl halide. When alkyl halide are heated with a large excess of sodium or potassium, hydrosulfide thiols are formed. HSNA positive react with RX give on heating gives alkane thiol RSH plus NaX. Example, HSK positive potassium hydrogen sulfide react with alkyl halide to form on heating to form alkane thiol from sodium alkyl sulfate or para-toluene sulfonic ester. When sodium alkyl sulfate is heated with sodium hydrogen sulfide, thiols is formed. HSNA positive on react with sodium methyl sulfate gives methane thiol CH3SH plus Na2SO4. Ethyl para-toluene sulfonate react with NaSH on heating gives ethane thiol C2H5SH or sodium para-toluene sulfonate CH3 C6H5SO3Na. Third is from alcohol. Mercaptan are prepared from alcohol either by treating with the phosphorus pentasulfide or by passing a mixture of hydrogen sulfide and alcohol vapor over thiourea catalyst at 673 Kelvin. 5 ROH or plus P2S5 on heating gives 5 moles of RSH plus P2O5. Alcohol on react with H2S in the presence of THO2 at 673 Kelvin temperature gives RSH plus H2O. Example, 5CH3CH2OH on reacting with P2S5 on further heating we get 5CH3CH2SH ethene thiol plus P2O5. Methanol on reaction with H2S in the presence of THO2 at 673 Kelvin we get methane thiol CH3SH plus H2O. From alkene, addition of hydrogen sulfide to the carbon-carbon double bond of an alkene in presence of nickel sulfide as catalyst led to the formation of thiol. Alkene on reaction with H2S in the presence of NiS at 573 Kelvin. Markovnikov addition, we get 2 alkane thiol or CH3 and SH. The addition occurring in accordance with Markovnikov rule, terminal thiols can however be prepared by free radical addition of H2S to an alkene. Alkene on reaction with H2S in the presence of light anti-Markovnikov addition are CH2SH1 alkane thiol. From thiourea or S-alkyl isothioureanium salt. When alkyl bromide or iodide are treated with thiourea, S-alkyl isothioureanium salt are produced. These upon alkaline hydrolysis give thiol in about 80 to 90% yield. Thiourea on tautomerism give enol form and on further reaction with RBR gives S-alkyl isothioureanium bromide. On alkaline hydrolysis we get RSH and urea. This is the best method for preparing thiol. From Grignard reagent, the reaction of Grignard reagent with sulfur powder gives addition product which upon hydrolysis gives thiol. Grignard reagent on reacting sulfur gives addition product RSMgX which on further hydrolysis gives alkane thiol and MgOHX. Physical properties, physical states, smell, etc. Methane thiol is a gas while other thiols are colorless volatile liquid with disagreeable smell. The lower member have actually strong smell while higher members have mild odor. The odor of freshly cut onion is due to propane 1 thiol and that of garlic is partially due to propane 2 in 1 thiol CH2 double bond CH2SH. Small quantities of ethane thiol are ID2 LPG to warn against leakage of the gas. Second is boiling point. Due to the absence of hydrogen bonding, the boiling point of lower thiol alcohol have lower than those of the corresponding alcohol. However, thiols have 8 or more carbon atoms have slightly higher boiling point than corresponding alcohol due to stronger van der Waals forces of attraction and weaker hydrogen bond. Third is solubility. Thiol are less soluble in water than the corresponding alcohol. This is due to the reason that thiol cannot form hydrogen bond with water. Fourth is dipole moment. Due to small electronegativity of sulfur and oxygen, SH bond is less polar than OH bond. As a result, thioalcohol have lower dipole moment than their corresponding alcohol. Chemical reaction. The thiol resemble alcohols in many ways. The main difference is their behavior is towards oxidizing agent. Some important chemical reaction of thiols are discussed below. First is acidic nature. Thioalcohol are stronger acid than alcohol. Is that pK value of ethane thiol is 10.5 while that of ethanol is 15.5. This is because of the following two reasons. The bond dissociation energy of SH bond is 347.3 kJ is much lower than those of OH bond 464.4 kJ. As a result, SH bond is cleaved more easily than the OH bond. The anion left after the removal of a proton from RSH is that RS negative has a negative charge on sulfur atom, while in case of alcohol, RO negative is on oxygen atom. Because of the larger size of sulfur, RS negative can accommodate the negative charge more easily than the smaller oxygen atom in RO negative ion. Some important reaction of thiol due to their acidic nature are discussed below. First is reaction with alkalis. Due to their stronger acidic nature, they dissolve in alkalis is that in NaOH or KOH forming their corresponding salt called mercaptides. The reaction is reversible and the mercaptides are completely hydrolyzed by water in the absence of alkali. RSH on reaction with NaOH gives RS negative and a positive plus H2. Reaction with mercury oxide being acidic thiol react with mercuric oxide to form mercury mercaptide. RSH plus HGO gives RS whole twice Hg plus H2O. Action of alkali metal. Alkyl metal being stronger base react with mercaptan to form the corresponding mercaptide with the evolution of H2 gas. RSH plus Na gives RS negative, Na positive plus H2. Action of heavy metal salt. When a thiol is heated with the aqueous solution of the salt of a heavy metal is at lead acetate, a mercaptide is obtained. RSH plus PbOOCCS3 whole twice gives RS whole twice Pb plus H3COOH, lead mercaptide. RS whole twice Pb. These heavy metal mercaptide are generally covalent compound. Second is reaction of carboxylic acid. Thiol react with carboxylic acid preferably in the presence of an inorganic acid as catalyst to form the corresponding thioester. Ester acid on reaction with thiols to give thioester. The equilibrium lie mainly to the left, however a good yield of an ester is obtained if acid chloride is used instead of acid. Third is oxidation. Due to weaker SH bond, thiols can be easily oxidized. The nature of the product, however, depend upon the nature of the oxidizing agent used. With mild oxidizing agents such as ZrH2O2, CuCl2 or sodium hypochlorite NaOCl, thiols are oxidized to dialkyl sulfide. RSH plus H2O2 gives dialkyl disulfide. RSSR plus 2 moles of water. An alkaline solution of sodium plumbite containing sulfur doctor solution also convert thiol to dialkyl disulfide. Dialkyl disulfide can also be prepared by the action of iodine on sulfur on sodium mercaptide with strong oxidizing agents such as HNO3, periodic acid, etc. Thiols are converted into sulfonic acid. This gives us an important point of difference between thiol and alcohol in their behavior towards oxidation. Whereas in alcohol, oxidation increases the oxidation state of carbon, while in the case of thiol, the oxidation state of sulfur increases. Reduction. On treatment with tin nickel, thiol readily undergo desulfurization to form the corresponding hydrocarbon. RSH in the presence of tin nickel gives alkyl and alkyl halide, alkene and on NIS. Action of aldehyde and ketone. Thiols readily combine with aldehyde and ketone in the presence of hydrochloric acid to form mercaptol or thioacetal and mercaptol or thioketal respectively. For example, acetaldehyde on reaction with ethene thiol gives diethyl methyl mercaptol A thioacetal. Acetone on reaction with HCS3CH2 in the presence of acid gives diethyl dimethyl mercaptol. When these mercaptols and mercaptols in ethanol are refluxed in the presence of nickel, the thiol group is replaced by hydrogen. Thus, mercaptol and mercaptol formation in acidic medium followed by disulfurization with nickel gives us an excellent method for conversion of a carbonyl group to methylene group under neutral condition. This method is, however, competitive with Clemmensen reduction, which is carried out acidic condition, and Wolff-Kishner reduction, which is carried out under basic condition. Further, this mercaptol and mercaptol on treatment with mercury chloride in the presence of cadmium carbonate regenerate the original aldehyde and ketone. Therefore, like acetal and ketal, mercaptol and mercaptol can also be used for protection of the aldehyde ketone group in the acidic medium. Oxidation of mercaptol. Mercaptol are easily oxidized to sulfonal. For example, oxidation of acetone mercaptol with KMnO4 gives sulfonal. Acetone mercaptol on reaction with KMnO4 gives sulfonal. Sulfonal is used as an hypnotic sleeping inducing drug, homologous of sulfonal, namely trianal and tetranal are even more effective hypnotics. Thioethers. Thioethers may be regarded either as trialkyl derivative of H2S or alkyl derivative of thioalcohol. They may also be regarded as derivative of ethers in which oxygen have been replaced by sulfur. Diethyl ethers on reaction with after removing oxygen on adding sulfur gives diethyl thioethers. Nomenclature. The common name of thioethers are obtained by adding the word sulfide or thioethers to the name of the alkyl group arranged in alphabetical order. In the apex system, thioethers are all named as alkyl thioalkane. The sulfur atom is taken with the smaller alkyl group which formed a part of the alkyl thio group, while the larger group form a part of the alkene. The common within parentheses and IUPAC name of the some thioethers are given below: CS3 SCS3, methyl thiomethane, dimethyl sulfide, CS3 SCH2 CS3, methyl thioethane, CS3 CH2 SCH2 CS3, ethyl thioethane, CS3 SCH2 CH2 CS3, methyl thio 1 propane, CS3 CH2 S CH3 CH2 CS3, ethyl thio 2 butane. Method of formation: by heating potassium sulfide with an alkyl halide, potassium alkyl sulfate or potassium tosylate. Potassium sulfide on reaction with alkyl halide gives thioether. Potassium alkyl sulfate on reaction with K2S gives thioethers. K2S on reaction with alkyl tosylate gives thioethers, and the yield are generally good to fairly good. By heating an ether with potassium pentasulfide, ether on reaction with P2S5 on heating give thioethers. The yield are often poor. By heating an alkyl halide with sodium mercaptide, we get thioethers. Sodium ethyl mercaptide on reaction SN2 mechanism gives ethyl methyl sulfide. This method is similar to Williamson synthesis and can also be used for the synthesis of both symmetrical and asymmetrical thioethers. Since alkyl sulfide is a better nucleophile than alkoxide ion, the reaction is very rapid and gives excellent yield. By addition of a thiol to an alkene in the presence of peroxide, peroxide gives R-COO negative O free radical, gives 2R alkyl free radical and CO2. By passing a thiol over a mixture of heated alumina and zinc sulfide at 573 Kelvin, thiol on reaction with ZnS plus Al2O3 at 573 Kelvin gives thioether or H2S gas. Example: ethane thiol on reaction with ZnS plus Al2O3 at 573 Kelvin give diethyl sulfide. Physical properties: physical state: thioethers are colorless, oily liquid having unpleasant smell. Solubility: they are insoluble in water but soluble in organic solvents such as alcohol, ethers, etc. Boiling point: in general, their boiling points are relatively higher than those of corresponding ether. This is due to stronger van der Waals forces of attraction in thioethers as compared to ether, primarily due to the bigger size of sulfur than oxygen atom. Chemical reaction: although ethers are relatively unreactive, thioethers are quite reactive. Their reactivity is primarily due to the ability of the divalent sulfur atom to get converted into compound with +4 and +6 oxidation state. The main difference lies in the formation of sulfoxide and sulfone on oxidation and to form sulfonium salt with alkyl halide. Some of their important chemical reactions are described below. First is one basic weak basic character. Due to the presence of lone pair of electron on the sulfur atom, thioethers like ether behave as a weak basis. As such, they dissolve in 100% H2SO4 to form sulfonium salt. R2S on reaction with H2SO4 gives R2S positive HSO4 negative. Second reaction with alkyl halide: being sufficiently nucleophilic, thioethers react with alkyl halide by SN2 mechanism to give trialkyl sulfonium salt. A noteworthy feature of sulfonium salt is that they are tetrahedral, the orbital containing the lone pair of electron being considered as a 4 substituent. If the 3 substituents attached to the sulfur atom are different, sulfonium salt behaves as chiral molecule and have been resolved into stable enantiomers. It may be noted here that tertiary amides of the type R1, R2, R3 and could not be dissolved in spite of the fact that they also have tetrahedral structure. The reason cited was that the energy difference between the two enantiomers was quite low, 25 kJ per mole, and thus rapid 2.3 into 10 raised to power 10 second inverse interconversion between the two enantiomers give a racemic mixture. However, in case of sulfonium salt, the energy difference between the two enantiomers is sufficiently high and hence cannot be readily interconverted. Therefore, sulfonium salt can be easily resolved. These sulfonium salts are stable at room temperature but decompose on heating to alkyl sulfide and alkyl halide. With moist silver oxide, this sulfonium salt forms sulfonium hydroxide which are strong base. R3S positive X negative on reaction with HgOH gives R3S positive OH negative plus AgX. This sulfonium hydroxide decomposes on heating to form the original alkyl halide, alkyl sulfide and alkene. For example, triethyl sulfonium hydroxide on heating give diethyl sulfide and ethylene. This reaction may occur either by E2 and E1 mechanism depending upon the nature of the alkyl group. If all the groups are primary, the reaction occur by E2 mechanism. If however one of the group is tertiary, the reaction occur by E1 mechanism. For example, third is the formation of sulfur halide and their reaction. The sulfonium salt on treatment with a strong base such as N-butyl lithium eliminate an alpha hydrogen to form dialkyl sulfonium methylide, commonly known as sulfur halide. For example, dimethyl sulfide on reaction with alkyl halide to give trimethyl sulfonium iodide. These sulfur halide are extremely useful synthetic reagent and have been widely used for the synthesis of epoxide and cyclopropane derivative by reacting them with a ketone or an activated olefin as shown below. Dimethyl sulfonium methylide A sulfur halide on reaction with ketone gives activated olefin styrene. Oxidation. Thioethers on oxidation first give sulfoxide then sulfone. Dialkyl sulfide on oxidation gives sulfoxide and on further oxidation gives sulfone. With mild oxidizing agent like HiO4 at 273 Kelvin, oxidation can be stopped at the sulfoxide stage. For example, dimethyl sulfide on reaction with HiO4 at 273 Kelvin gave dimethyl sulfoxide. With moderate and strong oxidizing agent, with moderate oxidizing agents such as H2O2 is glacial acetic acid, diethyl sulfide gives first diethyl sulfoxide and then diethyl sulfone. However, with strong oxidizing agents such as KMnO4, HNO3, etc., sulfones are directly obtained. Reduction. Alkyl sulfoxide on treatment with nickel readily undergo reduction and desulfurization forming alkane. Reaction with bromine. Alkyl sulfide form many addition products. For example, addition of bromine give dialkyl sulfide dibromide. R2S reaction with Br2 give R2SBr2. Sulfonic acid. Sulfonic acid are organic compound having the general formula RSO3H, where R may be at R may be an alkyl or aryl group. Dialiphatic sulfonic acid are named either as alkyl sulfonic acid or as alkane sulfonic acid, while aromatic sulfonic acid are named only as arene sulfonic acid. For example, CS3SO3H, methyl sulfonic acid or mercaptan sulfonic acid, CS3CH SO3H, isopropyl sulfonic acid or 2-propane sulfonic acid. Method of formation. Aliphatic sulfonic acid. Aliphatic sulfonic acid are generally prepared by the following method. First is oxidation of thiol. Thiol on oxidation with HNO3, KMnO4, NaOBr, etc. undergo oxidative coupling since SH bond are much weaker than OH bond to form first dialkyl sulfide, which under the condition of the reaction are further oxidized to alkyl sulfonic acid via thiosulfate ester or via sulfonic acid and sulfinic acid as shown below. Dialkyl sulfide on further oxidation give a thiosulfonate ester. Further on oxidation give a disulfide. Again on further oxidation give a sulfonic acid. Similarly, thiol on oxidation gives a sulfinic acid and on further oxidation give a sulfinic acid and on further oxidation give a sulfonic acid. Sulfonation of alkane. Sulfonation of alkane with concentrated H2SO4 oleum or chlorosulfonic acid gives alkane sulfonic acid. The sulfonic acid group generally enter the chain at second carbon atom is at an hexane on reaction with H2SO3 at 2H2SO4 on reaction with H2SO4 at 330 Kelvin gives hexane to sulfonic acid. Third, action of sulfuryl chloride on alkene. The action of sulfuryl chloride or a mixture of Cl2 and SO2 on an alkene in the presence of light or peroxide at 330 13 to 323 Kelvin gives the corresponding alkane sulfonyl chloride in high yield. Here again the SO2Cl group enter mainly at the second position of the chain, through a varying amount of product with this group at the first carbon are also formed. N-hexane on reaction with SO2Cl2 in the presence of light gives CH3CH2CH2SH CH3SO2Cl2. 2-hexane sulfonyl chloride major product and 1-hexane sulfonyl chloride is a minor product. Sticker reaction. Sodium salt of sulfonic acid are obtained when an alkyl halide is heated with sodium sulfite. Rx on reaction with Na2SO3 on heating give RSO3 Na plus NaX. Addition of sodium bisulfite to alkene. In the presence of oxygen or peroxide, anti-Markovnikov addition of sodium bisulfite to alkene give the sodium salt of the corresponding alkane sulfonic acid. For example, CH3CH double bond CH2 on reaction with NaHSO3 in the presence of oxygen or peroxide at 298 Kelvin, anti-Markovnikov addition gives sodium propane sulfonate. Aromatic sulfonic acid. Aromatic sulfonic acid are prepared by the sulfonation of aromatic hydrocarbon with concentrated H2SO4, fuming sulfuric acid, sulfur trioxide, and 1-proto-pyridinium sulfonate. C5H5N plus SO3. Benzene on reaction with H2SO4 SO3 gives benzene sulfonic acid. Toluene on reaction with H2SO4 gives para-toluene sulfonic acid major, and ortho-toluene sulfonic acid is a minor product. Furan on reaction with the C5H5N plus SO3 gives furan 2 sulfonic acid. The choice of the sulfonating agent and the condition employed mainly depend upon the type of the aromatic compound to be sulfonated. When the aromatic compound contains an activating group, the sulfonation is usually carried out with concentrated H2SO4 at relatively low temperature. In contrast, sulfonation of deactivated aromatic compound is carried out with fuming H2SO4 at high temperature 473 to 573 Kelvin. 1-proto-pyridinium sulfonate is mainly used for the sulfonation of acid-sensitive aromatic compounds such as furan, pyro, etc. Physical properties. First is aliphatic sulfonic acid are colorless liquid or low melting solid, while aromatic sulfonic acid are colorless crystalline solid, which are highly hygroscopic in nature. The melting point of sulfonic acid are lower than the corresponding carboxylic acid. This is because of the presence of hydrogen bonding in sulfonic acid, as a result of which they exist as discrete molecule, while the aliphatic carboxylic acid exists as cyclic dimer due to hydrogen bonding. Chemical reaction. Some important chemical reaction of sulfonic acid are discussed below. Acidic nature. Sulfonic acid are completely ionized. In the aqueous solution, they are strong acid as H2SO4. Sulfonate ion is a resonance hybrid of the following three equivalent resonance structure. As a result of negative charge is dispersed on all the oxygen atom, and hence sulfonic acid are strong acid. In contrast, the carboxylate ion is stabilized by the two equivalent resonating structures. Therefore, carboxylic acid are weaker acid than sulfonic acid. Being acidic, sulfonic acid neutralize alkalis and decompose carbonate and bicarbonate, evolving CO2 gas. Formation of acid chloride. When treated with thionyl chloride or phosphorus pentachloride, they form the corresponding sulfonyl chloride. This sulfonyl chloride on treatment with ammonia or alcohol in the presence of alkali or better with sodium alkoxide form the corresponding sulfonamide and sulfonic ester respectively. Alkyl sulfonyl chloride on reaction with ammonia give alkyl sulfonamide. Third is the formation of anhydride. On heating with phosphorus pentoxide, sulfonic acid form the corresponding anhydride. Replacement reaction of arene sulfonic acid. A number of reagent can bring about the replacement of sulfonic acid group by other group. This is because sulfonic acid is an excellent leaving group. This property makes sulfonic acid as valuable reagent in organic synthesis. A few important reactions of this type are discussed below. First is replacement of OH group. When sodium benzene sulfonate is fused with alkali, sodium phosphoride is produced. Replacement by NH2 group. When sodium arene sulfonate are fused with sodamide, primary aromatic amines are formed. Replacement by CN group when fused with NaCN, sodium salt of aryl sulfonic acid gives aryl cyanide. Replacement by SH group. Sodium aryl sulfonate on fusion with sodium hydrosulfide give thiophenol. Replacement by hydrogen desulfonation. Sulfonation follow the principle of microscopic reversibility. Thus, when aryl sulfonic acid are reacted with dilute HCl under pressure at 423 to 473 Kelvin, aryls are produced. The mechanism of desulfonation is just reverse of sulfonation as shown below. Replacement by a halogen atom or a nitro group. When a sulfonic acid gives group is located at ortho or para position with respect to the OH or the NH2 group, it is knocked off and replaced by NO2 group or X atom during nitration and halogenation respectively. For example, paraphenol sulfonic acid on reaction with HNO3 on heating gave 234 give picric acid, and sulfonic acid on reaction with Br2 HNO3 gives 246 tribromophenol. Sulfonamide. Sulfonamide are derivative of sulfonic acid in which OH part of the sulfonic acid SO3H group has been replaced by NH2 group or the substituted amino groups such as NHR and NR2. For example, sulfonamide C6H5SO2NH2, N-methylbenzene sulfonamide C6H5SO2NHCS3, and N-dimethylbenzene sulfonamide C6H5SO2NCS3 whole twice. Preparation. Sulfonamide are generally prepared by the action of ammonia primary and secondary amine on the corresponding sulfonyl chloride. For example, benzene sulfonyl chloride on reaction with ammonia give benzene sulfonamide. C6H5SO2Cl on reaction with methylamine give N-methylbenzene sulfonamide. Properties. Sulfonamide are well defined crystalline solid and are therefore used to characterize sulfonic acid. Acidic nature. They are weakly acidic in nature and hence they react with strong alkali to form water soluble salt. For example, benzene sulfonamide on reaction with KOH give potassium benzene sulfonamide. Hydrolysis. Sulfonamide on heating with aqueous acid or alkali undergoes hydrolysis to form the corresponding sulfonic acid. Benzene sulfonic acid on reaction with the water on further heating in the alkali medium gave benzene sulfonic acid. Uses. They are used in the manufacture dye antiseptics such as chloramine T and sulfa drug. Sulfaguanidine H2 NH2 C6H5 SO2 NH C double bond NH NH2. Synthesis. Acetanilide on chlorosulfonation with excess of chlorosulfonic acid give para-acetoamidobenzene sulfonyl chloride, which upon further treatment with guanidine following by the acidic hydrolysis gives sulfaguanidine. Aniline on reaction with CS3CO whole twice O H2SO4 few drops give acetanilide. On further reaction with ClSO3H, after removing water we get para-acetoamide benzene acetamido sulfonyl chloride. Para-acetamido benzene sulfonyl chloride. On further reaction with guanidine NH2 C double bond NH NH2 we get CH3CONH C6H5 SO2 NH C double bond NH NH2. On further acidic hydrolysis we get sulfaguanidine NH2 C6H5 SO2 NHC double bond NH NH2. Guanidine needed for the purpose itself prepared by heating cyanamide with ammonium chloride. Cyanamide gave guanidine or HCl. Uses. Sulfaguanidine is an important sulfa drug and is used for treatment of biliary dynatry since it is only slightly absorbed in the intestinal tract. Therefore, it is given in relatively large doses. Synthetic detergent. These days, in place of soap, the substances which are being largely used as glazing agent are synthetic detergent. As the name suggests, they are obtained from purely synthetic chemical as compared to soap, which are derived from chemical obtained from natural sources like oil, fat. In fact, synthetic drugs are sodium or potassium salt of long chain alkyl hydrogen sulfate or aryl sulfonic acid. Unlike soap, synthetic detergent can also be conveniently used even in the hard water. This is due to the reason that calcium and magnesium salt of detergent like their sodium or potassium salt are also soluble in water. Hence, synthetic detergent do not form curdy white precipitate with hard water. Further, they can also be used in the acidic solution. However, synthetic detergent have one disadvantage. Unlike soap, they are not completely biodegradable and even causes water pollution. The typical synthetic detergent are either sulfate or alkyl benzene sulfonate. First is the sodium alkyl sulfate. They are obtained from long chain alcohol by treatment with concentrated H2SO4 followed by neutralization with NaOH. Some important example of this type of detergent are sodium lauryl sulfate, C11H23CH2OSO3 negative and positive, and sodium stearyl sulfate, C17H35 CH2OSO3 negative and positive. Sodium lauryl sulfate is also commonly known as sodium dodecyl sulfate SDS. It is mainly used in shampoos and cosmetic. Lauryl alcohol on reaction with concentrated H2SO4 give lauryl hydrogen sulfate. On further reaction with NaOH gives sodium lauryl sulfate. This sodium alkyl sulfate are 100% biodegradable. These are also effective in slightly acidic solutions since they form an alkyl hydrogen sulfate which is a soluble material, whereas soap react with the acidic solution to form insoluble fatty acid. Alkyl benzene sulfonate, the most commonly used domestic detergent these days are linear alkyl benzene sulfonate (LAS), which are such as sodium para and dodecyl benzene sulfonate. They are anionic detergent and are obtained by conversion of benzene into long chain alkyl benzene followed by sulfonation and neutralization with NaOH. For example, benzene on reaction with CS3 CH2 whole 10 SO sorry CS3 CH2 whole 10 COCl anhydrous AlCl3 Friedel-Crafts acylation gives and and dodeca dodecanoyl benzene. On further reduction in the presence of ZnHg, HCl Clemens reduction gives and dodecyl benzene. On further reaction with concentrated of sulfonation gives P and dodecyl benzene sulfonic acid. On further reaction with NaOH, by removing water molecule we get sodium para and dodecyl benzene sulfonate. Another important example is sodium para 2-dodecyl benzene sulfonate. It is prepared by Friedel-Crafts alkylation of benzene with a long chain alkyl halide or an alkene or an alcohol followed by sulfonation and neutralization with NaOH. For example, 1-dodecane from petroleum source on reaction with benzene in the presence of anhydrous AlCl3 Friedel-Crafts acylation gave 2-dodecyl benzene. On further reaction with concentrated H2SO4 and NaOH gives sodium para 2-dodecyl benzene sulfonate. Alkyl benzene sulfonate, in which the phenyl group is either attached to the end of the long alkyl chain or any other secondary position, have higher biodegradability and hence are called soft detergent, while alkene benzene sulfonate having branch chain alkyl group have poor biodegradability and hence are called hard detergent. Cleansing action of soap and detergent. All the soap and detergent contain two characteristic groups, is that a water soluble hydrophilic group and an oil soluble hydrophilic or lyophilic group. As a result, one end of the molecule or a soap or detergent tends to go into oil phase and other end tends to go into the water phase, with the net result that the material soap or detergent concentrate at the surface of the solution or interface. Lyophilic part C17H35 and S double bond O negative and positive is hydrophilic part. The dirt is generally held to a dirty surface by a thin film of an oil or grease. When the dirty surface is treated with soap solution, the non-polar hydrocarbon chain of the soap or detergent dissolve in oil or grease and the Carboxylate group of the soap or the sulfonate group of the synthetic detergent is held by surrounding water. This lowers the surface tension between the water and grease. As a result, the stable emulsion of oil in water is formed. When the surface of the cloth is mechanically scrubbed, the loosened dirt particles are absorbed by colloidal soap or detergent particle and ultimately washed away. Thank you.